Module 8, Lecture A, Image AI Concepts. By the end of this lecture, you will be able to represent image-style civil engineering data as NumPy arrays and pixel grids, explain convolution, filters, pooling, and simple CNN architectures conceptually, and implement small manual filter operations and visualize their effect with Matplotlib. Image arrays. Pixel grid basics. A digital image is a grid of pixels, where each pixel stores information about one point in a scene, such as brightness or color. In civil engineering, this could represent a bridge deck photo or a drone image of a construction site. Computers use these pixel values as numerical arrays, which makes it possible to store, analyze, and process visual information. An image's pixel grid preserves spatial relationships, so each row and column corresponds to a position in the scene. This structure lets computers connect parts of an image to real-world areas, such as top regions or bottom regions, and analyze nearby pixels to detect patterns like cracks or stains. Understanding the grid links what we see visually with how images are processed as arrays. Images can be represented as numerical grids, but the values depend on the image type. A grayscale image stores one brightness value per pixel, while a color image stores separate red, green, and blue values, and engineering images may store data such as elevation or heat intensity. This grid structure makes visual information easier to analyze and automate. Python code, pixel grid basics. Pixel grids represent images as numbers, with rows and columns keeping track of each pixel's location. Even small arrays can store simple inspection images in this structured form. The script begins by importing NumPy for efficient numerical work with arrays and calculations, and Matplotlib Python for creating plots and displaying images. Together, these libraries provide the basic tools needed for data processing and visualization. A small grayscale pavement section is represented as a two-dimensional NumPy array, where each value gives a pixel's brightness. Higher values mean lighter areas, while lower values mean darker areas. Most values gradually decrease in brightness, but two much lower values in the second row likely indicate dark pavement features, such as cracks. The code defines a grayscale image as a two-dimensional grid of pixel brightness values. Each row contains numbers, where higher values are brighter and lower values are darker. The values gradually decrease across rows to create a gradient, making it easier to inspect and manipulate pixels, including darker areas that may represent cracks or other features. We first check the pavement grid's shape to confirm its number of rows and columns. An assertion then verifies that the grid is 6 by 6 before any plotting or further work begins. If the size is different, the program raises an error to prevent incorrect assumptions about the grid. We select a pixel that represents a dark crack in the pavement grid using row index 1 and column index 2, which points to the second row and third column. We then read that pixel's grayscale value, where a lower number means the pixel is darker. We first check the grid's shape to confirm its number of rows and columns. Then we inspect one pixel at a chosen row and column, which represents a dark crack in the grayscale image. Because lower pixel values mean darker shades, this value helps interpret the crack visually. Create a 5 by 5 inch plotting canvas with Matplotlib. Then display the pavement grid as an image on the axis. Use a grayscale color map and set the brightness range from 0 to 255, so the full range of gray values is shown. To show pixel boundaries, set minor tick marks along both axes at half-step positions around each pixel using NumPy's arrange function. These ticks are not labeled, but they guide the grid placement. Then enable the minor grid lines in yellow with a line width of 1, so each pixel is clearly separated. Set the horizontal ticks to match the grid's columns and the vertical ticks to match its rows, so each tick lines up with an array index. Label the axes as column index and row index to make the grid easier to interpret. A specific pixel in the NumPy grid is highlighted with a red outline to identify a dark crack in the pavement image. The plot title explains that the display is a tiny pavement image represented as pixel values, and a color bar provides a reference for the grayscale brightness levels. Finally, the code uses the Matplotlib show function to render the plot. This displays the pixel grid as a grayscale image, including the annotations and highlights added earlier. This script shows how a small grayscale image can be represented as a pixel grid. It uses a 6x6 array, where each value gives a pixel's brightness, then checks the grid size and highlights one dark pixel that represents a crack. The visualization displays the image with row and column labels, a brightness color bar, yellow pixel boundaries, and a red outline around the selected dark pixel. Pixel grid basics. A digital image is a grid of pixels, where each pixel represents a small part of a scene. In civil engineering, visual data such as drone images and thermal scans can be analyzed through this grid structure. This helps engineers identify spatial patterns, such as dark pixel patterns from concrete cracks or bright lines from lane markings. Computational image analysis treats an image as an array of pixel values. In grayscale images, each value represents brightness, so patterns can reveal features such as cracks or stains. In color images, each pixel stores red, green, and blue values, allowing materials like rust or fresh asphalt to be distinguished. This makes an image a structured numerical dataset for analysis, not just something to view. Pixel grids define an image's resolution and shape what image analysis can reveal. More rows and columns can show finer details when sensing conditions are good, while lower resolution captures broader features. Because each pixel is only a sample affected by lighting and sensor quality, results must be interpreted carefully. In civil engineering, responsible image AI treats these grids as simplified models that connect visual data to computation. Python code. Pixel grid basics. Images can be understood as pixel grids that store visual engineering information. NumPy arrays make those pixels measurable, and small examples help reveal the structure inside an image. The script begins by importing two key Python libraries, NumPy for numerical work with arrays and matrices, and Matplotlib's plotting tools for creating visualizations. Together, these libraries prepare the script for computation and graphical output. We create a small grayscale image of a bridge deck using a NumPy array to store pixel brightness values. Each number represents a pixel's intensity, forming a simple two-dimensional image that can be analyzed and visualized later. Two rows of a NumPy array are used to model a small grayscale image section of a bridge deck. Their brightness values shift from bright areas to very dark pixels and then back to medium brightness, suggesting a crack-like defect between solid surface regions. The second row follows the same pattern with slightly different intensities, adding realistic variation. The code defines a small two-dimensional NumPy array that represents part of a grayscale bridge deck image. Each value is a pixel brightness from 0 for black to 255 for white. The array has 6 rows and 6 columns, uses 8-bit unsigned integers, and the shown portion includes its last 2 rows. We validate the pixel grid before using it by confirming it is 6 by 6 and stored as 8-bit unsigned integers. This ensures the grayscale pixel values are in the expected range from 0 to 255, helping avoid errors during image processing or display. We first check the grid shape to confirm the image dimensions, then inspect the brightness of 1 pixel at row 2, column 2. Finally, we count how many pixels have brightness below 60, which can help identify dark, crack-like regions that may suggest structural issues. Create a 5 by 5 inch Matplotlib figure with axes. Then display the pixel grid using the axes image display function. Use a grayscale color map and set the brightness range from 0 to 255, so the full pixel value range is shown accurately. To label the pixel grid, set tick marks on the x-axis for each column and on the y-axis for each row, using NumPy to generate the needed positions. This aligns the labels with the grid structure, making the plotted image data easier to read and interpret. The plot is given a clear title identifying it as a tiny grayscale bridge deck pixel grid. The horizontal axis is labeled by column position and the vertical axis by row position, helping viewers understand the grid's layout and orientation. To label each pixel with its brightness, the grid is scanned row by row and column by column so every pixel is reached. For each pixel, its brightness value is read, converted to an integer, and placed on the plot at the matching position. The text is centered within each pixel to make the values easy to read. Add a color bar to show the image's brightness range, from dark values near 0 to light values near 255. Then adjust the layout so plot elements fit cleanly without overlapping, and display the final image with its annotations on screen. This script shows how to represent a small grayscale image as a 6 by 6 pixel grid for a bridge deck. It checks that the grid has the correct size and unsigned 8-bit data type, then reports basic information such as the grid shape, 1 pixel's brightness, and how many pixels are dark enough to suggest possible cracks. Finally, it displays the grid as a grayscale image with brightness values labeled on each pixel, a color scale, row and column labels, and a civil engineering title. Pixel Grid Basics. A digital image can be understood as a grid of pixels, where each pixel stores information about one location in a scene. In civil engineering, data such as drone images and thermal scans can be treated this way, with rows and columns defining position and pixel values describing local details. This turns images from simple pictures into structured data that computers can analyze and transform. Images are stored as numerical grids of pixel values. In grayscale, each pixel represents brightness, while color images use separate red, green, and blue values. In civil engineering, these values can reveal defects, material changes, and spatial patterns, but meaningful analysis depends on interpreting both the numbers and their relationships across the image. Images are numerical arrays of pixels, and their arrangement affects how we interpret scale, detail, and location. Higher resolution reveals small features, such as cracks or textures, while lower resolution is more useful for broad shapes, like building outlines. Because image coordinates often start at the top left, they must be handled carefully when connecting pixels to real-world map locations. This understanding supports later work in filtering, analysis, and machine learning. Python code, Pixel Grid Basics. Images, can be represented as grids of numbers, where each row and column identifies a pixel's location. The number at each position describes that pixel's brightness or visual intensity. We import NumPy to work with the numerical array data that represents the image grid. We also import Matplotlib's plotting tool so the grid can be displayed as a grayscale image, making the pixel data easier to understand visually. We create a small 6x6 grid of numbers to represent a grayscale image. Each value gives a pixel's brightness, with larger values meaning brighter pixels. The grid uses unsigned 8-bit integers, the standard range for image data, from 0 to 255. This simulates a tiny bridge deck image patch, where brightness changes may suggest cracks or shadows. Before visualizing an image grid, confirm that it is a two-dimensional array and that it contains data. These checks ensure the grid has the expected structure and help prevent errors when displaying it. Set each image pixel to represent 2.5 centimeters, giving the grid a real-world scale. Then identify the grid's number of rows and columns, so its layout can be used for tasks such as plotting or processing the image. The code summarizes the image array by reporting its grid size and the range of pixel brightness values. It also gives the real-world scale, with each pixel representing about 2.5 centimeters. Darker pixels may suggest cracks or shadows in the image. A 5 by 5 inch plotting area is created. Then the image grid is displayed as grayscale data. The display uses a gray color map and sets the brightness range from 0 to 255, so the full range of pixel intensities is shown correctly. Add a clear title to identify the tiny grayscale pixel grid. Then label the horizontal axis as the column index and the vertical axis as the row index. These labels show how the grid is organized and make each pixel's position easier to interpret. To show pixel positions clearly, set the axis ticks to match the image dimensions, columns along the x-axis and rows along the y-axis. Then add a yellow grid with thin lines to separate the pixels and make the grid structure easier to see. The process visits every pixel in the image grid by moving through each row and column. For each pixel, it reads the brightness value and chooses a contrasting text color, white for darker pixels and black for lighter ones. It then places the brightness value centered in the matching cell, so the label remains easy to see. A color bar is added to connect the grayscale image to its brightness intensity values, making the pixel shades easier to interpret. The layout is then tightened so the plot elements fit neatly, and the plot is displayed for visual inspection. This script uses NumPy and Matplotlib to display a small grayscale image as a grid of pixel brightness values. It defines a 6x6 image, checks that the data is valid, and reports its size and value range. The plot shows the image in grayscale with row and column labels, pixel values inside each cell, a grid for clarity, and a color bar for brightness. This makes it easier to spot patterns, dark regions, or possible anomalies in the image data. CNN building blocks. Convolution filters. Convolution filters help neural networks understand images by scanning small regions of pixels and responding to patterns they recognize. Early layers detect simple features like edges, lines, and color changes, while deeper layers combine these signals into more complex patterns. This lets the network build meaning from local details instead of processing the whole image at once. Convolution filters work by applying the same small detector across an image. helping a network find important features wherever they appear. This makes them useful for tasks like detecting pavement cracks or steel corrosion. Reusing filters improves efficiency and preserves spatial information, producing feature maps that show where patterns are detected strongly or weakly. In a trained convolutional neural network, filters are learned from data rather than designed by hand. As training progresses, early filters become sensitive to simple visual patterns, such as edges and color changes, while deeper layers combine these signals into more complex textures and shapes. This helps the network build image understanding in stages. But the filters still detect patterns rather than meaning, so their results need careful validation and expert interpretation in engineering work. Python code. Convolution filters. Convolution filters find local patterns in images by sliding small kernels across the pixel grid. The resulting feature maps highlight where those patterns produce stronger responses. We import NumPy for efficient numerical work with arrays and math operations. We also import Matplotlib's plotting module to create and display clear visualizations of images and data. A simple grayscale image is created as a blank 12 by 16 array, then filled with a few brighter regions to form a bridge-like pattern. Two horizontal bands of different brightness levels create the main structure, while three brighter vertical lines act as supports. Together, these elements produce a basic synthetic image resembling a bridge. A diagonal feature is added by selecting several rows and placing a dark pixel one column to the right of each row position. Setting these pixels to a low value creates a crack-like diagonal line in the image. This makes the pattern more complex for convolution analysis. A vertical edge detection filter uses a 3 by 3 matrix with each row containing -1, 0, and 1. This pattern highlights left-to-right changes in pixel intensity, so it responds strongly to vertical lines in an image. The apply filter function takes an image's pixel grid and a filter kernel as inputs. It first records the number of rows and columns in both the image and the kernel. These dimensions provide the basic setup needed before applying convolution. The convolution process first checks that the filter is a 3 by 3 matrix, since the function is built for that size. It then creates a zero-filled output grid to store the results. Because the filter cannot move beyond the input grid's edges, the output has 2 fewer rows and 2 fewer columns than the original pixel grid. The convolution scans the pixel grid with a 3 by 3 patch, stopping before the edges, where the patch would not fit. At each position, it multiplies the patch values by the kernel values and sums the results. Each sum is placed into the output array, gradually forming the feature map. The function returns an output array containing the convolution results for the input pixel grid. Each value represents the filter's computed response at a specific location, showing the local patterns detected there. A vertical edge detection filter is applied to the image by sliding it across each region and computing the convolution. This creates a feature map that highlights strong vertical edges. Taking the absolute value of the feature map makes all edge responses positive, so the strength of the detected features is easier to interpret. The output summarizes the convolution process by showing the image size, the filter size, and the resulting feature map size. It then reports the strongest edge response found as the maximum value in the feature strength map and rounded to 2 decimal places. This value indicates the most prominent pattern detected by the filter. A figure is created with 3 side-by-side subplots to compare the original image, the filter, and the convolution response. The first subplot shows the grayscale image with intensity values limited between 0 and 1 and is titled Civil Image Grid. The second subplot displays the vertical edge detection filter using a contrasting cool-warm color map and is titled Vertical Edge Filter. The second subplot is labeled to show the vertical edge filter used to detect vertical edges. The third subplot shows the strength of the resulting feature map with a magma color map, making the intensity of detected patterns easier to interpret. To make the images clearer, each plot axis has its X and Y tick marks removed. This keeps attention on the image content and avoids distracting axis labels or markings, which makes the visualization better suited for teaching. The tight layout command in Matplotlib arranges subplots so they fit cleanly without overlapping. The show command then displays the figure, making it possible to view the images and titles. Together, these steps help you visually assess the convolution results and the effect of the filter on the image. This script shows how a convolution filter can find patterns in a grayscale image. It creates a simple image with a bridge-like shape and a diagonal crack, then applies a vertical edge detector using manual convolution. The resulting feature map highlights vertical edges and reports the strongest response. It also displays the original image, the filter, and the feature map to show how the filter emphasizes vertical patterns. Pooling layers. Pooling layers in convolutional neural networks reduce detail in feature maps while keeping the most important information. Max pooling keeps the strongest response in a small region, while average pooling summarizes the region by averaging its values. This helps the network focus on key patterns, such as cracks or edges in civil engineering images. Pooling makes neural networks more efficient by reducing feature map size and helping them recognize features within a region rather than at exact pixel locations. This gives the model some tolerance to small image shifts, which is useful for images captured under varied conditions. It also saves memory, speeds training, and helps deeper layers focus on broader patterns. Pooling in convolutional neural networks reduces early image features into broader patterns, making data simpler and easier to process. This is useful for classification, where exact pixel locations matter less, but it can remove details needed for precise tasks, such as measuring crack widths. Model design should therefore balance simplification with detail retention based on the accuracy required for the engineering decision. Python code, pooling layers. Pooling summarizes nearby feature responses, making small shifts in the input less important. This helps create more robust representations, which is especially useful for still images that may vary in position or appearance. We import NumPy to work efficiently with the numerical arrays used in the feature map. We also import Matplotlib's plotting tools so we can visualize the feature maps and the results of pooling operations. We create a small two-dimensional feature map using NumPy's array function. Its grid of values represents initial data, such as image or sensor information, that can be processed with pooling to reduce size while keeping important features. This section defines 3 rows of a two-dimensional array that represent part of a feature map. The values capture local feature activations across a spatial grid. Together, these rows form a region used in pooling, where local features are summarized to reduce dimensionality and make the representation more robust to small shifts. This line completes a two-dimensional NumPy feature map by adding the final row of values. The array is set to use floating point numbers, which supports later operations that need numerical precision, such as pooling with averages or maximum values. First, get the feature map's height and width. Then check that both are even. This matters because pooling splits the map into 2x2 patches, so even dimensions ensure every element fits cleanly into a patch. If either dimension is odd, the pooling step may leave elements out or cause errors. The pooling function processes the input in 2x2 windows. It creates an output array with half the input's height and width, then fills it with either the maximum or average value from each window. The array is scanned in steps of 2 across both rows and columns, so each pass selects a 2x2 block. Each block is a small patch of the feature map, which is then summarized through pooling. This code summarizes each 2x2 patch of the feature map based on the selected pooling mode. In max mode, it keeps the largest value to emphasize the strongest local feature. Otherwise, it uses the average value, producing a smoother summary of the local area. The function returns the pooled output array, which contains the max or average pooling results from the input feature map. This returned data can then be used for further analysis or visualization elsewhere in the program. Max pooling and average pooling both summarize a feature map using 2x2 regions. Max pooling keeps the highest value in each region, highlighting the strongest local evidence, while average pooling takes the mean, producing a smoother summary. In both cases, pooling reduces the feature map's spatial size and makes the information more compact. We compare the original feature map with the results after max pooling and average pooling by looking at their shapes. Both pooling methods reduce the data size, but they summarize it differently. Max pooling keeps the strongest local signals, while average pooling creates smoother, more generalized summaries. A 3-panel figure is created to compare pooling results side by side. The panels display the original feature map, the max pooled version, and the average pooled version, making it easy to see how each pooling method changes the data. The visualization labels 3 panels as feature map, max pooling, and average pooling. A loop displays each corresponding image with Matplotlib's image display function, using the Viridis color map and a shared color range from 0 to 8 for consistency. Each subplot is then given its title, so the panels are easy to identify. The code removes the tick marks and labels from both axes by setting the X and Y ticks to empty. This creates a cleaner plot and keeps attention focused on the image itself. A shared color bar is added to show the range of activation strengths consistently across all panels. Its size is reduced to fit the layout, and it is labeled Activation for clarity. The layout is then tightened to prevent overlap, and the completed figure is displayed on screen. This example shows how pooling reduces a feature map while preserving important information. Starting with a 6x6 map, max pooling selects the strongest value in each small region, while average pooling takes the mean, producing smoother results. Both methods shrink the map to 3x3, and the visualization compares the original with the 2 pooled versions to show how pooling summarizes local features for tasks such as image recognition. Dense layers. Dense layers in a convolutional neural network combine the features found by earlier convolution and pooling layers into a final decision. Earlier layers detect and summarize patterns such as edges, textures, and lines, while the dense layer learns how these signals relate to each other, In a bridge deck image, this helps the network judge whether the combined visual evidence suggests normal wear or possible damage. Dense layers connect each unit to all outputs from the previous layer, combining features rather than focusing on their original location. In image classification, they often serve as the decision stage, turning extracted visual patterns into categories. This helps models recognize cases such as helmet use or structural conditions by bringing earlier features together into a final judgment. Dense layers are powerful because they learn flexible mappings from many features, but their many parameters can also cause overfitting. For this reason, they are often kept small and placed after convolution and pooling layers to reduce complexity. Their outputs should be treated as model predictions, not human explanations, so engineers must still review the context and check for possible errors, such as when assessing suspected damage in a retaining wall. Python code dense layers. Dense layers combine visual features into a final interpretation. In this simple example, the features are small and manually defined, so no machine learning library is required. We import NumPy to work efficiently with numerical data using arrays, matrices, and mathematical operations. We also import Matplotlib's plotting module to create visualizations that help interpret the results of our computations. The content defines simple bridge deck features such as dark lines, rough texture, and color change, then stores their measured strengths in a numerical array. The values 0.85, 0.60, and 0.30 represent how strongly each feature is present and are kept as floating point numbers for accurate later calculations. Validate the input by confirming it has exactly 3 features, since the dense layer expects 3 values. Also ensure each feature is between 0 and 1, so the inputs stay normalized and calculations remain consistent. This code sets up the weights and biases for a dense layer with 2 units and 3 input features. Each dense unit has 1 weight for each feature, so both units are fully connected to the inputs. A separate bias value is also assigned to each unit, and these biases are added to the weighted input sums to help adjust each unit's output. Before matrix multiplication, confirm that the layer dimensions match. The weight matrix should have 2 rows and 3 columns representing 2 dense units connected to 3 input features, and the bias vector should have 2 elements to match those units. These checks ensure the calculations can proceed correctly. Dense scores are computed by combining the input features with their weights and adding a bias for each dense unit. The result is a score for each possible output. Labels then give these scores meaningful names, such as possible crack or surface staining, so the dense layer output can be interpreted as specific conditions or classifications. To turn dense layer scores into probabilities, use a stabilized softmax process. First, subtract the largest score to avoid overly large exponentials. Then exponentiate the adjusted scores to make them positive. Finally, divide each value by the total so the results add up to 1 and can be interpreted as probabilities. The output first summarizes the dense layer inputs by matching each feature with its rounded value. It then shows each label's dense layer score, also rounded for readability. Finally, it selects the label with the highest probability and prints it as the predicted class. We create a Matplotlib plot to show how each dense unit weighs the input features. The weights are displayed as a color image using a cool to warm color scale to separate negative and positive values. The color range is fixed from -1.2 to +1.2, so the weights are shown consistently and clearly. To make the plot easier to interpret, Tick positions are created for both axes, so each feature and label has a matching location. The x-axis ticks are labeled with the feature names and rotated slightly for readability, while the y-axis ticks are labeled with the corresponding label names. This clearly connects each axis position to the correct feature or label. To make weight values readable inside the plot cells, loop through the rows and columns of the weights array and place each value in its matching cell using Matplotlib's text placement method. Format each value to one decimal place and center the text both horizontally and vertically for clear viewing. The plot is labeled to show that each dense layer output connects to every input feature. A color bar helps interpret the strength and direction of the connection weights, while the layout is adjusted so the visualization is clear and uncluttered. The final display lets viewers see how dense units relate to the input features. This script demonstrates a simple dense layer without using a machine learning library. It takes 3 bridge deck features, applies weights and biases in 2 dense units, and turns the resulting scores into probabilities for 2 classes, possible crack or surface staining. It prints the features, scores, and predicted class, while a heat map shows how each unit weights the inputs. Together, the output and visualization show how dense layers combine feature information to make a prediction. Simple CNN architectures. Manual filter operations. Manual filter operations give a simple view of how convolutional neural networks process images. An image is treated as a grid of pixel values, and a small filter moves across it to produce a new output by responding to local patterns. The filter does not understand objects like a person would. It only highlights matching pixel arrangements, such as edges or textures, which is useful for interpreting visual data in civil engineering. Applying an image filter means moving across the image and comparing small regions of pixels. Edge filters highlight changes in brightness, such as vertical changes from left to right or horizontal changes from top to bottom. Other filters can blur an image to reduce noise or sharpen it to bring out detail. Overall, image processing transforms pixel grids into clearer representations using local numerical operations. Plotting the output of a manual filter helps turn raw numbers into a visual map of detected patterns. Bright areas show strong matches, while dark areas show weak or missing matches. This makes filter behavior easier to interpret in real images, but it also shows a key limitation. Filters can respond to shadows, noise, or other non-structural features, not just the patterns we want. Python code, manual filter operations. Manual filters can highlight local patterns in images. Even small arrays can represent simple image structures, and comparing different filters shows how each one changes or emphasizes features in the image. We import NumPy to handle numerical data efficiently with arrays and mathematical operations. We also import Matplotlib's plotting tools so we can display images and graphs, helping us visualize how different filters affect the synthetic image. We create a simple synthetic pavement image as a 40 by 40 pixel square grid. Every pixel is set to a medium gray value of 0.65 using NumPy's full function, forming a uniform background that can later be modified to represent features such as cracks or lane markings. To simulate a vertical crack in the synthetic pavement image, selected pixel columns are darkened. A full-height dark line is created by lowering 2 adjacent columns to a low intensity, and a shorter, slightly lighter line is added nearby, over a limited range of rows. Together, these changes create the appearance of a crack, or similar pavement feature. A bright lane marking is added by setting a small rectangular area of the image to a high-intensity value, making those pixels appear lighter. Afterward, the pixel values are clipped to stay between 0 and 1, which prevents invalid intensity values and keeps the image data consistent. 3 simple 3x3 filters are used for basic image processing. A vertical edge filter highlights changes between neighboring columns, while a horizontal edge filter highlights changes between neighboring rows. A blur filter gives equal weight to all 9 nearby pixels, averaging them to smooth the image and reduce sharpness. The apply filter function manually applies convolution to a grayscale image using a given kernel. It first gets the image dimensions so it can process the image data, then checks that the kernel is a 3x3 matrix. This size check helps ensure the filtering operation runs correctly. To perform the convolution, we first create a zero-filled output array to store the results. Because a 3x3 kernel cannot be centered on the image borders, the output is 2 pixels smaller in both height and width. We then scan the non-border pixels, and at each position, take the surrounding 3x3 patch to compute the convolution value. To compute convolution at 1 pixel, a 3x3 image patch centered on that pixel is multiplied element by element with the filter kernel. The multiplied values are added together to produce one filtered value, which is placed in the matching position of the output. Repeating this process produces the full filtered image array. The image is processed with 3 filters using the apply filter function, which performs convolution. The vertical edge filter highlights left to right intensity changes, while the horizontal edge filter highlights top to bottom changes. The blur filter averages nearby pixels, reducing sharpness and creating a smoother image. The code first checks the size of the synthetic pavement image to confirm the grid dimensions. It then shows how different filters affect the image. The vertical filter detects left to right intensity changes, the horizontal filter detects top to bottom changes, and the blur filter smooths the image by averaging nearby pixel values. A single figure is created with 4 side-by-side panels using Matplotlib subplots. Each panel is given a title for the original image, vertical edges, horizontal edges, and blurred result. The corresponding images are then placed in these panels so the effects of the filters can be compared directly. The code loops through each subplot, title, and image together. For each one, it shows the image in grayscale, adds the matching title, and hides the axes to create a cleaner display. A figure-level title is added with the Matplotlib subtitle method to describe the overall theme. Manual filter operations on a pavement-like pixel grid. The tight layout method then adjusts spacing so the subplots fit cleanly without overlap. Finally, the show method displays the completed figure for visual inspection. This example shows how simple filters affect a synthetic grayscale pavement image with a crack and a lane marking. A vertical edge filter detects left to right intensity changes, while a horizontal edge filter detects top to bottom changes. A blur filter averages nearby pixels to smooth the image and reduce sharpness. Comparing the original with these filtered results helps show how filters reveal or modify local image patterns. Activation maps. An activation map shows where an image filter responds most strongly as it scans across an image. Filters can highlight patterns such as vertical edges, horizontal changes, cracks, or material differences by making those areas stand out. This helps learners focus on important visual details that may be hard to notice in the original image. Plotting activation maps helps make filter behavior easier to understand by showing where a filter responds strongly in an image. Light areas in a grayscale map indicate high responses, such as edges, cracks, or window frames. However, filters detect pixel patterns rather than meaningful objects, so bright regions do not automatically signal damage or risk. Interpreting these maps requires context, image quality, and careful judgment. Activation maps show where a filter detects patterns in an image, connecting manual filtering with convolutional neural networks. In manual filtering, the filter is chosen by hand, while in a neural network, filters are learned from data, but still create maps that reveal what they respond to. Early layers usually detect simple features like edges and textures, while deeper layers combine them into more meaningful patterns. These maps help explain what the model is focusing on, making its behavior easier to interpret. Python code, activation maps. Activation maps reveal how filters respond to visual patterns, while synthetic pixels can represent civil imagery. Manually working through convolution helps build intuition for how these visual features are detected. We import NumPy to work efficiently with numerical data in arrays and matrices. We also import Matplotlib's plotting tools so we can display images and activation maps to visualize the data and computation results. A synthetic pavement image is created as a two-dimensional gray array with a uniform background value of 0.35. A lighter vertical strip is then added in the center by raising those pixel values to 0.85, representing a feature such as a road marking or lane divider. The synthetic image is updated by changing selected pixel intensities to create simple lane markings. A brighter horizontal band is added across part of the image, and a darker vertical line is added so it intersects the band. Together, these changes simulate basic road features in the image. Two basic edge-detecting filters can highlight changes in image intensity. A vertical filter uses negative values on the left, zeros in the center, and positive values on the right to detect vertical edges. A horizontal filter uses the same idea from top to bottom to detect horizontal edges. Both filters work by emphasizing differences between neighboring pixel values. Before applying the edge detection filters, we validate the inputs. The image must be two-dimensional. Both vertical and horizontal filters must be 3x3 matrices, and the image must be at least 3 pixels wide and tall so the filters fit within its boundaries. The function first determines the size of the activation map for a valid convolution. It does this by comparing the pixel grid size with the kernel size, so the kernel is only placed where it fits completely inside the grid. This gives the number of possible row and column positions while avoiding boundary issues. An empty activation grid is created to store the convolution results. The filter is then moved across each valid position in the image, where a 3x3 image patch is selected. For each patch, its values are multiplied with the filter values and summed into one response, which is saved in the matching position of the activation grid. The function takes the absolute value of the activation array, so every value in the activation map is non-negative. This highlights the strength of each filter response without considering its direction, making the convolution results easier to interpret. We compute two activation maps using valid convolution on the synthetic pavement image. One uses a vertical edge filter to highlight vertical features, and the other uses a horizontal edge filter to highlight horizontal features. Comparing these maps shows how each filter responds to different edge patterns in the image. We summarize the edge detection results by checking the image size, the activation map size, and the strongest responses from the vertical and horizontal filters. The maximum activation values rounded to 2 decimal places show where each filter detected the strongest edge. Together, These outputs give a quick sense of how well the convolution filters captured vertical and horizontal features in the synthetic pavement image. The visualization is set up as 3 side-by-side plots in one row. It shows the synthetic pavement image next to the vertical and horizontal activation maps, making it easy to compare the original image with the results of the convolution operations. For each axis and plot item, the grid is displayed as a grayscale image using the image display function, with pixel interpolation turned off. The axis title is then set from the provided title, so each grid is clearly labeled with its context. The code removes the tick marks and labels from both axes. This makes the image display cleaner by eliminating distracting numbers and grid markings. To finish the visualization, use Matplotlib's tight layout function to clean up the spacing between subplots. Then display the figure so you can compare the original synthetic image with the activation maps for vertical and horizontal edges. This script shows how convolution can detect edges in a simple synthetic road image. It creates a small pixel grid with lane markings, then applies vertical and horizontal edge filters by sliding them across the image to produce activation maps. The strongest responses reveal where vertical and horizontal edges appear, and the script reports key dimensions and maximum activations before displaying the original image alongside the results. Filter visualization. Filter visualization shows how a small filter pattern moves across an image's pixel grid to create a transformed version. Some filters emphasize brightness changes to reveal edges or cracks, while others smooth variations to reduce noise. Comparing the original and filtered images helps learners see which details are preserved or changed, and how raw pixels become useful patterns for AI models. Each filtered image acts like a response map, showing where a filter detects a particular visual pattern. Some filters emphasize vertical or horizontal changes, while others sharpen details or smooth textures to reveal larger shapes. Brighter areas mean a stronger match to the filter's pattern. This helps connect manual image filtering to convolutional neural networks, where many filters combine to detect more complex features. When visualizing filter effects, the display settings matter because contrast, color mapping, and scaling can change how the same data appears. Adjusting the display range can reveal patterns, while grayscale emphasizes intensity, and color maps can make subtle differences easier to see. In civil engineering, these images highlight selected features, such as cracks, but they do not prove structural problems on their own. Good filter visualization means asking what the transformation reveals or hides before making engineering judgments. Python code filter visualization. This section shows how filters respond to a small pavement image. By applying manual convolution, you can see how each filter detects local pixel patterns, and a comparison plot highlights the different responses. We begin by importing NumPy to work efficiently with image data as arrays and to perform mathematical operations such as convolution. We also import Matplotlib's plotting tools to display the original image and the filtered results, making it easier to compare how each filter changes the image. A synthetic 18 by 18 grid is created to model pavement intensity, starting with a uniform value of 0.55. A darker horizontal strip is added by lowering part of the grid to 0.25, and a brighter vertical feature is added by raising several columns to 0.75. These simple patterns provide a controlled image for testing filter responses. The image array is edited to add 2 simple features: a bright vertical stripe representing a lane marking, and a smaller medium-intensity patch near the bottom right. After these changes, A check confirms that the image still has its intended 18 by 18 shape. Three basic image filters can be defined as small 3 by 3 arrays. A vertical edge filter compares the left and right sides of a region to highlight vertical changes, while a horizontal edge filter compares the top and bottom to highlight horizontal changes. A blur filter averages the surrounding pixels in the same size region, smoothing the image and reducing detail. The apply filter function prepares for manual convolution by reading the dimensions of both the grid and the kernel. It then checks that the kernel is a 3 by 3 matrix, which is the required size for the operation that follows. Convolution creates a smaller output grid by sliding a 3 by 3 filter across the image. At each position, it takes the matching 3 by 3 image patch, multiplies it element by element with the filter, and adds the results. That sum becomes the output value for that location, representing the filter's response there. The function returns an output array that represents the filtered image. It contains the new pixel values produced by applying the convolution filter, highlighting features such as edges or blurred areas depending on the filter used. The image is processed with 3 filters to measure different responses. A vertical filter highlights vertical edges, a horizontal filter highlights horizontal edges, and a blur filter smooths the image by averaging nearby pixels to reduce detail and noise. Manual filters turn pixel data into response maps that highlight specific image features. Edge filters produce bright responses where local changes are strong, such as along boundaries. Blur filters smooth fine details while preserving larger regions, helping reduce noise and emphasize broader patterns. A single row figure with 4 subplots is created to compare the original image with 3 filtered results. The layout is made wide enough for clear side-by-side viewing, and each subplot is given a title: original, vertical edges, horizontal edges, and blur. The corresponding images are then organized so the effects of each filter can be displayed and compared easily. The code loops through each subplot, title, and image together, displaying each image in grayscale to highlight intensity differences. It adds a descriptive title to each subplot, such as original or vertical edges, and removes axis markings, so the images appear clean and easy to compare. Matplotlib is used to tidy the plot layout so the images do not overlap. Then display the final figure for inspection. This makes it easier to compare the original image with the filtered versions and see how each filter changes the result. This script shows how manual convolution changes a synthetic pavement image. It applies vertical edge, horizontal edge, and blur filters to an 18 by 18 grayscale grid that represents pavement and lane markings. The edge filters highlight strong changes in intensity, while the blur filter smooths details and preserves broader regions. Displaying the original and filtered images side by side makes it easier to compare how each filter emphasizes or softens different patterns. In this lecture, you learned to, first, represent image-style civil engineering data as NumPy arrays and pixel grids. Second, explain convolution, filters, pooling, and simple CNN architectures conceptually. And third, implement small manual filter operations and visualize their effect with Matplotlib. Congratulations on completing this course.
Thank you for your attention. See you all in the next lecture.